Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about uncorrelation and independence. Our goal is to explain the difference between two random variables being uncorrelated and two random variables being independent. The prerequisites for this material are independence of random variables and correlation between random variables. Let us begin by reviewing what we have learned about correlation. The correlation coefficient between two random variables A and B is defined as the covariance between A and B, which is just the expected value of the product between the random variables after centering, after subtracting the respective means, divided by the standard deviation. Okay, so we normalize the covariance by the standard deviation, we get the correlation coefficient, which we have learned is between -1 and 1 and quantifies the linear dependence between A and B. In particular, if A and B have zero mean and unit variance, then if we try to obtain the best linear estimate of B given A, then the best linear estimate in mean squared error is equal to A scaled precisely by the correlation coefficient. If A and B are not standardized, so their mean is not 0 and their variance is not 1, or their variance is not 1, then if we look at the relationship between the standardized versions of A and B, which are centered and normalized, by subtracting their corresponding means and dividing by their corresponding standard deviations, then if we try to estimate the standardized version of B using the standardized version of A using a linear estimate, then the best linear estimate is obtained by, again, scaling by the correlation coefficient. So here we're saying that the correlation coefficient between A and B is exactly the same as the correlation coefficient between the standardized random variables. So we quantify linear dependence by looking at the relationship between the standardized counterparts of the random variables. Okay, so when the correlation coefficient and the covariance are positive, that means that the linear estimate of one random variable given the other has a positive slope. Okay, the standardized version of the random variable is to some extent proportional, directly proportional to the standardized version of the other random variable. And that's reflected again by this positive slope in the linear estimate. If that slope is negative, then we say that the two random variables are negatively correlated. And if that slope is 0, that basically means that when we try to estimate one random variable given the other linearly, we give up and we say the best estimate is 0. Here it's 0 because we have standardized both random variables. If there weren't 0 mean, then we would just estimate B as the mean of B. Okay, we would just say we cannot obtain a better linear estimate than a constant using this other random variable because they're not linearly dependent. That's what it means for two random variables to be uncorrelated. It turns out that if two random variables are independent, then that implies that they're also uncorrelated. To see this, we only need to look at the covariance. The covariance between two random variables can be written as the expected value of the product minus the product of the expected values. This can be derived from the definition just by linearity of expectation. And now we know that this term, when two random variables are independent, is just equal to the product of the means. So the two terms are the same, they cancel out, and when two random variables are independent, they are always also uncorrelated, which makes a lot of sense. If there's no dependence between the two random variables, in particular, there is no linear dependence. What about the converse? You know, like if two random variables are uncorrelated, does that mean that they're also independent? Let's take a look at an example. Okay, in this example, the joint distribution of two random variables A and B is given by this joint PMF, which is only non-zero at 3 points, at 0, 0, 1, 1, and 1 minus 1. Okay, and the area of each of these markers represents the value of the joint PMF there. So it's equal to 1/4 at 1, 1, 1/4 at 1 minus 1, and 1/2 at the origin, at 0, 0. Okay, so let's start by seeing whether these two random variables are uncorrelated. So the first thing we're going to do is we're going to estimate the mean of B, which can be obtained by summing the possible values of B times the corresponding values of the joint PMF. So for 1/2, B is 0, for 1/4, B is -1, and for 1/4, B is 1. When we add this up, the mean of B is 0. So now when we compute the covariance is the expected value of the product between A and B minus the product of the means. Because one of the means is 0, the covariance is just equal to the expected value of the product of the two random variables. This product can be equal to 0, 1, or -1. It's equal to 0 with probability 1/2, -1 with probability 1/4, 1 with probability 1/4. So this again cancels out, and we see that the covariance is 0. The two random variables are uncorrelated, which makes a lot of sense, because if you imagine here trying to estimate A from B, you can't really do much better than, well, here of course you're going to say, if you see that A is 0, you're going to say that B is 0. Here, if you see that A is equal to 1, then you can't really choose between 1 and -1. So you might as well choose 0, right? And in mean squared error, actually, this is going to be optimal because that's the conditional mean. We will come back to that point in a moment. Okay, so clearly, you cannot find a better linear estimate than just saying, this line. There's no other line that is going to be better in mean squared error. Okay, so now we could ask ourselves, are they independent? Are A and B independent? In order to determine whether they're independent, let's consider the conditional PMF of B given A. If A and B are independent, then the conditional PMF given any value of A will be the same. So what's the conditional PMF of B given A? Given A equals 0, sorry. I'll give you a moment to think about it. Well, if A is equals to 0, B is always equal to 1. So this is a very simple PMF where the probability of B equals 1 given A equals 0. Sorry, the probability of A equals B equals 0 given A equals 0 is equal to 1. Okay? Sorry about that, I got myself confused. I just went up the stairs like 10 minutes ago and I live on the 11th floor. I'm a little bit out of breath and I guess my brain is not getting enough blood. Okay, too much information probably. The thing is that the distribution of B given A equals 0 is just very simple. It's a PMF which is equal to 1 at 0 and 0 everywhere else. Is this the same PMF when A is equal to 1 with condition on A equals 1? Not at all, right? Not at all. If A is equal to 1, then B is equal to either 1 or -1 with probability 1/2. Because remember, we take a slice of the PMF and then we have to renormalize by the probability that A is equal to 1, which is equal to 1/2, in order to obtain a valid conditional PMF. So the conditional PMF is going to be 1/2 on 1 and 1/2 on -1. Clearly, they are not independent. They are in fact completely dependent. Actually, something interesting is you could ask yourself, okay, they're not independent. What is the best minimum mean squared error? Minimum mean squared error estimator. If you want to minimize mean squared error, what is the best estimator? So we know that that's the conditional mean. And in this case, the conditional mean is equal to 0 if A is equal to 0. And if A is equal to 1, it's also 0. So this linear estimate, which gives up and says like, okay, I think, if you want to estimate B from A, just say it's 0 all the time. This linear estimate is actually optimal in this case, which shows you, something else. It shows you that even if the best nonlinear estimate in terms of mean squared error is linear, that doesn't suffice to, that doesn't mean that the two random variables are independent. Okay, here we have an example where they're clearly not independent, and the best nonlinear estimate in terms of MMSE is actually linear, and it's equal to a constant that is equal to 0 in this case. Okay, so uncorrelation does not imply independence, and this is something that we see all the time when we apply, when we compute correlations in practice. So we had this example where we're looking at rebounds against height, and we saw that rebounds are essentially proportional to height, so they're positively correlated. If we subtract the linear estimate of rebounds given height from the original data, okay, that's the original data, we obtain this residual. And we proved in a previous video that the residual, so the residual, just to be clear, is on this y-axis. Okay, that's b minus the linear estimate. That is uncorrelated with height. We showed that. And actually you can see, right, that the shape here is kind of proportional in a way, and this has been corrected. Okay, this guy has been, has been shaped again, like reshaped, so to say, like rotated a bit, so that the linear relationship is not there anymore, at least on average. But if we think of the conditional distributions of the residual given height, then clearly there is no independence, right? So here, for example, you see that this slice is going to give, it's going to be completely different to this other slice, okay? So in general, when we're applying, when we're computing correlations from real data, if we look at our residuals, very often they will be uncorrelated, but they will show us that there is nonlinear relationships within the data that we're not accounting for, and this is obvious in this residual here if you look at these slices. Another example from real data, this is a scatter plot of rain against maximum temperature, monthly maximum temperature against monthly rain in Oxford over like 100 years or something. We see that rain and temperature are essentially uncorrelated, but if we look at the conditional mean, we see that in this case the conditional mean is actually different, and that when it's very hot, it turns out that rain and maximum temperature just in this region are negatively correlated. But it turns out that when you consider all of the data and you see what the linear dependence is on average, there is no linear dependence on average. So this is another example where we see real data which indicates that the two random variables are uncorrelated, or rather the quantities that are represented by these random variables are uncorrelated, but they're definitely not independent. Okay, so now let's finish by talking about Gaussian random variables, which are a very, very special case. So we're going to consider a Gaussian random vector with zero mean and covariance matrix equal to this. To make things simple, we're considering two Gaussian random variables that have unit variance, and zero mean. But what we're going to establish for them would hold for general Gaussian random variables. We have already seen in a previous video that we can interpret this parameter rho as the correlation coefficient between the random variables. And if we look at the contour lines of the Gaussian random variables, their ellipses and their shapes are determined by rho. In particular, when rho is equal to 0, so the correlation coefficient is equal to 0, we get these circular contours of the Gaussian random variables. Now, we know that these two random variables are going to be uncorrelated in this case because we have shown that the correlation coefficient is equal to this parameter rho, so if rho is 0, correlation coefficient is 0, the random variables are uncorrelated. We can ask ourselves what happens with this conditional distributions if we start slicing the joint PDF. Okay, so we could slice it at a minus 1, a equals 0, a equals 2, and we can take a look at these conditional distributions and see how they look. Just to be very clear about what we're doing, the joint PDF would come up here, and now we would take slices, okay, to see what the values are at minus 1, 0, and 2. And remember that we have to renormalize these guys to make them, this is maybe some good reviews about, a good review about conditional distributions. We still need to renormalize these guys so that the area under the 1D curve is equal to 1 and they're a valid PDF. So let me show you what these guys look like after this normalization. And what happens is that they look exactly the same. So for Gaussian random variables, when the ellipse becomes a sphere, or a circle in 2D, the ellipsoid becomes a sphere in higher dimensions, what tends to happen is, well, not what tends to happen, what happens is that uncorrelation actually implies independence. Let us show this for our example. Okay, our simple example where the variances are 1 and the mean is 0. So this is the general expression for the PDF or the joint PDF of a Gaussian random vector. In our example, we had this choice of covariance matrix, and again, what we're going to show generalizes directly to Gaussian random variables that have non-zero mean and non-zero and variances that are different from 1. And what we've said is that the correlation coefficient is 0. Okay, so let's see what the implications are for the joint PDF of the Gaussian random variables. The inverse of the covariance matrix is just equal to the identity, because here we're plugging 0 and 0, so we get that the covariance matrix is the identity. Its inverse is also the identity. When we plug it into the expression for the joint PDF of the Gaussian random variables, we obtain this. And now what happens is that there is no cross term, because the cross term was multiplied by the correlation coefficient, by the off diagonals of this inverse covariance matrix. Because there's no cross term, we can just separate this into two terms that are clearly equal to the marginals of A and B. So the joint PDF factorizes exactly into the marginal, to the product of the marginal PDFs, showing you that in the case of Gaussian random variables, uncorrelation implies independence. Okay, so what have we learned? We have learned that independence always implies uncorrelation. We have learned that uncorrelation generally does not imply independence. And we have also learned that for Gaussian random variables, it does. When Gaussian random variables are uncorrelated, they're also independent. Thank you very much.